of reactions. So when we talk about the enthalpy of reaction, energy is absorbed if it's endothermic. Well, what does that mean? That means delta H is positive, and delta H, when it's written, is greater than 0. Temperature decreases in an isolated system, and heat is absorbed in a non-isolated system. So if you're in an isolated system, then as the reaction occurs, it can't pull heat from anywhere else, so therefore the temperature is going to drop. If it's in a non-isolated system, what it's going to do is absorb whatever heat it can from around it. We refer to this as endothermic. Now, exothermic is when energy is given off. And delta H is negative, which means it's less than 0. Temperature will increase if it's an isolated system, and heat will be emitted, given off, etc., in a non-isolated system. Okay, and this is really easy if you think about it. If you take in any biology, you may have heard of the terms endoskeleton and exoskeleton. Who has an endoskeleton? You do. Humans have an endoskeleton because it's inside. Who has an exoskeleton? Bugs, beetles, roaches. When you step on them, they crunch because their skeleton is hard on the outside and they're gooey in the inside. Okay? So when we talk about enthalpy, what you need to remember is X means is exiting. Endo means is going inside. Okay? So keep that in mind. We're going to see that a variety of different ways. And this comes into play when we start talking about reactions. Because what we have here is energy is rising over here. And this is our equation. So this is our products. These are our reactants. So in this particular case, we started our reactants and we dropped down to our products. So energy is given off, so it is an exothermic reaction because energy is negative. Now, same reaction except let's flip it. We're going to go in reverse. So we're going to reverse the reaction. Energy is still going up. Our species H2 and O2 are still at this energy level, except now this is the reactants and this is the products because we flipped it. So now if you'll notice, we have the exact same energy value. So the number is the same. The only thing that changed is the sign. Now, does that mean that we'll always be negative and go positive? No. We'll sometimes have a negative exothermic reaction. Sometimes we'll have an endothermic reaction, meaning it's positive. The trick is if you flip the reaction, you flip the sign. It's a directionality. The sign is just like the interstate. If I tell you, and this isn't true, but it'd be nice, that somebody buried $1 million and all you have to do is get on the interstate, go 100 miles, and get off the exit and dig there. Works, except do you go north or do you go south? North and south on I-75 are directionality. So the biggest thing is that we have to be able to look at it with respect to a directionality. Okay? So when we look at it, if you're visual, your initial system is always your level. And if we go to a lower system, we're giving off energy. If we're moving to a higher energy, we're going to a higher potential energy. So that means that you had to gain energy to go up, and you give off energy to go down. So if you're a visual directionality, there you go. Now, That brings us to state functions. They're dependent upon the state of the systems. Okay, if I could spell the system. It's just too exciting. I was system. Okay? So, a state function is dependent on the state of the system. It is independent of path. It is strictly the change which is equal to the final state minus the initial. Okay? If you noticed when we were doing delta G is equal to Q plus W, Q and W were small letters and delta E was a capital, as is delta H. And the reason why is if they're a capital letter, that denotes that they are a state function. So if you see something that's a capital, it's a state function. If it's a lowercase letter, then it's not a state function. So if you think about it, as we've been doing things, I've been making a big deal about, big letters and little letters, and there's a reason why. So let's talk about the enthalpy of the system. That's the measure of the amount of energy transferred in a chemical reaction or process. So you're going to transfer energy back and forth. Sometimes it's chemical reaction, sometimes it's process. And so the enthalpy is equal to the energy plus pressure volume. Well, pressure and volume change. If you do that, that's work. So E is the internal energy of the system. PV is the pressure volume work that can be done. Okay? Now, the trick is how do you measure internal energy? Well, it's kind of hard because when they take a temperature, when you go somewhere and they take your temperature, what that is they're measuring a variety of systems going on in your body. Now, if you've been sitting in a hot car and you get out and you take your temperature, it's going to be warmer because your body was sweating to try to cool off. If you're sitting in a cold car and not moving, then your temperature is going to be a little bit lower because of the conditions around it. So sometimes it's much more important to look at the change because you may not be able to measure all the factors. So, for example, if I tell you to stand still right now, are you perfectly still? Maybe by appearances, but you may be breathing shallowly. I hope your heart's still beating, and you may have eaten dinner, so your stomach is doing its thing. So the bottom line is that on the outside you don't see all that movement, but it's in there. It's like a watch. You don't see any movement, but something's moving in there to keep time. So a lot of times it's better if we don't look at the initial amounts, but we look at the change because we can measure and see how far he's come. And one of the easiest things to measure energy wise is heat because energy is transferred in the form of heat. You'll reach out and feel something. It may be hot, it may be cold. Temperature measures relative hot and cold. So it might not be that it's real hot, but it may be hotter than it was before. So the kinetic theory of heat states that heat, when it enters the system, produces an increase in the average motion of all particles in the system. Okay, heat always flows from hot to cold. It's like items, they always roll downhill, high to low. Okay, there is no net flow when the temperatures are equal. So, as I said, that's why insulated cups will keep cold drinks colder longer than they will hot drinks because hot drinks are trying to escape. The heat is trying to escape, is actively trying to leave. Whereas in the cold, it's passive unless something comes in. Okay? So a closer look is energy, enthalpy, and pressure volume work. And if you look at this, you're like, wait, what is this? This is the cylinder, I could spell, in an engine. Well, it could be in any variety of things, but this is exactly how your pistons work in your car. So it may be worth reading over. So that brings us to bringing it back to reactants and products and a chemical reaction. So here we're back to equations. So the enthalpy of reaction is the measure of the amount of energy transferred in a chemical reaction or process. So remember, delta means final minus initial. So that means your final are going to be your enthalpy of your products, because that's your final position, over the enthalpy of minus the enthalpy of the reactants. So again, endothermic is when energy is absorbed. Delta H is positive, and delta H is greater than 0. Exothermic is when energy is emitted. Delta H is negative, which means it's less than 0. So this is actually the hard part. And if you've ever done any accounting, you talk about assets and debits. So if you think about it as money, if you're spending it, it's exothermic. If you're getting it, it's endothermic. So your paycheck would be endothermic and your phone bill is exothermic. Okay? So when we look at reactions, we've got to take a couple things into consideration. And so we're going to break these up and look at them individually. The first thing we're going to look at is that we have the physical states. So you're like, oh, we have the exact same reaction. We have hydrogen plus oxygen makes water. But the difference is on this one is this one's liquid and this one's gas. So if you think about it energy wise, the energy of a gas is up here, the energy of a liquid is down here, and the energy of a solid. These are closer to each other, but this one's going to be way different because remember, energy gases are in constant motion, etc. So if you'll notice that you're going to give off, so this means that it's emitted, and we're going to give off this much energy. But if you take it all down to liquid, then you're going to actually give up more energy because if you think about it, what you're doing is starting here. This may be water as a gas, and this is water as a liquid. So what you're looking at really is that the amount of energy drops to here from the reactants. It'd be nice if I leveled that off. And here if it's a liquid. So it drops to a lower position. So when we look at enthalpies of reaction, we have to worry about what state it's in. The other thing we have to take into consideration is how much do we have? The amounts, grams or moles. Now, it doesn't matter if you use grams or moles, but you have to be consistent. Okay? And if we're looking at using it in an equation, we really want it in moles. We can use it in grams, but then we have to convert it. So if we're looking here for this reaction, notice that this is the lowest ratio of the reaction. So this means that this all goes together, and this is a stoichiometric amount. But if you have 2 moles of hydrogen, then you're going to give off negative 241.8 kilojoules because that's what the equation states. But if we have 2 moles of oxygen, that means we would have to multiply everything by 2, and we would actually generate double that amount of energy given off as we go. Okay? So what that means is that we've got to consider not only physical states because of energy considerations, but we have to figure amounts. So the other thing we have to take into consideration, and we've actually talked about this one, is directionality. For every reaction, you have a directionality. It's going one way. So at least the reactions you're going to work with. Okay, so if we have this reaction is going forward, then these are the reactants, these are the products. So as written, it's negative. If we reverse it, then these become the products and this becomes the reactants. So now we're starting here and going back. So notice, again, we have the same number, but the sign flips. So if it was negative, it becomes positive. If it was positive, it becomes negative. It doesn't matter what you start with. What matters is that you flip it. Okay? So again, could be positive, goes negative, could be negative, goes positive. So let's work a problem. All right? So what you do to the equation, you're going to do to the enthalpy. So if you multiply the equation, you multiply the enthalpy. You flip the equation, you flip the sign. You divide, you divide. Okay? So it says write a thermochemical equation for the following formation of 1 mole of ammonia. So if we look at this, the original equation has 2 moles. So what we're going to do is we're going to divide it by 2, everything. It's like a mathematical process, so you divide everything. And we're still forming it, so that means ammonia is still a product, so we're good to go. So that means that it becomes 1/2 N2 plus 3/2 H2 yields NH3 gas. So remember, we divided the equation, so we're going to have to divide the final value. Now, notice that we kept the sign. That didn't change. And you're like, but you told us you can't balance equations with fractions. I didn't balance the equation with a fraction. What I did was I assigned a specific number of moles. And so then, yes, you end up with fraction. And yeah, it looks like splitting hairs. But notice we're not balancing, we're manipulating a balanced equation. Okay. So now we're going to decompose 4 moles. So you can go, it doesn't matter which one you do first. I'm going to work it left to right. Decomposition means that you're going to break it down. That means that NH3 will now be a reactant. What does that mean? That means we're flipping the equation. Okay? So that's the first thing. But then we have 4 moles of ammonia. Well, we only had 2 moles, so we're going to multiply it by 2. So when we do this to the equation, we're going to do both. We're going to flip it, which means the ammonia is now the reactant, and we're going to multiply it by 2. So we've got this, and so that means we have 2 N2 gases plus 6 H2 gases. And so if we're going to flip delta H, then it was negative, so it's going to become positive, and we multiplied it by 2, so we end up with double the amount. So now we ended up with positive 184.44 kilojoules because we flipped the sign, and we multiplied it by 2. Okay? So we'll do one more, combining 1 mole of hydrogen with the stoichiometric amount nitrogen. So if we look at the equation, wait a minute, we have 3 moles of hydrogen. Okay, we're going to combine hydrogen, so that means that hydrogen is a reactant. but we only need 1 mole of it. So that means we're going to end up with a third nitrogen. Whoops, I actually wrote that. Gas plus hydrogen gas yields 2/3 ammonia. And delta H is going to be negative still because we didn't flip it. But you are going to divide it by 3, so you get 30.74 kilojoules per mole. It happens to be per mole. Okay, so if you'll notice that we didn't use B to get C or A to get B, we always went back to our original equation to assume our values. Okay, because our values are critical to be maintained stoichiometrically. Okay, so what's that mean? That means equations are back. Okay, so we're going to calculate the energy change when 34.8 grams of pentaboron nonanhydride. You wouldn't have to name that, but okay, reacts with excess oxygen. So here's our overall equation. It is balanced. It's the lowest ratio. It's got a delta H that's negative. So we're going to convert, we want the energy change. So we want the change in energy. We're going to start with our amount, which is 34.8 grams of pentaboron nonanhydride. And we know that if we do our math, that it weighs 63.12646 grams, H9, per 1 mole. Okay, so I've canceled my grams. Now I'm at moles. So now I'm going to go through the equation. And I know according to the equation, there are 2 moles of B5H9. Now, wait a minute. From here, we would either be searching for B2O3 or water if we were working with gram amounts or mole amounts. But we're not. We need energy. So then, according to the equation, for 2 moles here, we're going to get negative 8686.6 kilojoules of energy off. So we would run the math, our moles cancel, and so anything on top is multiplied and anything on the bottom is divided. So we end up with negative 2394.35 kilojoules. Well, looking at it, we have 3 significant figures, so we would report it as negative 2390 kilojoules. So that was relatively easy. So let's do it again, except this time we want the energy difference when B2O3 is combined with water to form. Wait a minute. So this was a product, so now this is going to become a reactant, which means the sign will flip. Okay? So again, 27.5 grams. We're going through an equation, and just remember that every time you think equation, think moles. So 1 mole of B2O3, so diboron trioxide, is 69.6202 grams of diboron trioxide. Okay, so our grams cancel, we're left with moles, and we know according to this equation, we're going to have 5 moles of B2O3. But for every 5 moles, we are going to get 86.6. But it was negative. We're going to flip the sign, so now it's going to be positive. So when we do the math, everything on top is multiplied. Everything on the bottom is divided. We're going to end up with this value here. We again have 3 significant figures, so it's plus 8. No, if I could copy my own stuff, plus 686 kilojoules. would be my final answer. Now, is it important that you put the positive in? Again, my recommendation is put the positive in, because if you put the positive in, then you're less likely to forget it when it's a negative. If you choose not to, then you're more likely to forget the negative. So it's just a good habit to be in. Okay? So the enthalpy change for sublimation of 1 mole of solid iodide at 25 degrees C and 1 bar. What's the 1 bar? Do we have to use it? No. It's just standard conditions for this. So this is our equation. What energy must be transferred to vaporize? Well, vaporize is the big term to go from a liquid to a gas. Okay? And this one is actually vaporizing. That would be a liquid. In the case gas, grams, so solid to a gas, that's actually sublimation. Sublimation is the technical term. But vaporizing, it is moving it basically from state to state. But yeah, I probably need to change that. Okay. So, wait. We want to know the energy. So we're going to vaporize 10 grams, 0.0, of iodide. Now, in this case, do I need to keep up with the solid? Yeah, because we're dealing with solid and gas. So we don't need to cancel the solid with the gas. Okay, so the molecular weight is 2/3. Whoops, can't read my stuff again. So it's 253.809 grams of iodide, solid, per 1 mole of iodide, solid. And so what we need to do is move it. So we're going to have 1 mole of iodide solid, 2 plus 62.4 kilojoules, because that's the energy associated there. So we do the math. We're going to get a positive 2.4585 kilojoules. We have 3 significant figures, even though I didn't write them. So it's plus 2.46 kilojoules is how much energy is transferred. Okay, so on B, it says if 3.42 grams of iodine vapor condenses to form solid iodide, that's actually deposition, but we're looking at the energy. So we're going to start with the 3.42 grams of iodide gas. We know that it's still 253.809 grams of iodide, whether it's gas or solid, per 1 mole of iodide. But in this particular case, we're going from the vapor, which is the gas, to the solid. So that means we're going in reverse, so we're flipping. So that means that we had a positive, so now it's 62.4 kilojoules per 1 mole of iodide. So that means that you get negative 0.84082 kilojoules, which again, 3 significant figures, 0.841 kilojoules. All right, and remember, you've reversed the equation, so you flip the sign. Okay, now, the question in C says, is the process in B exothermic or endothermic? Well, let's go back. So the original equation is positive, so that means that's endothermic originally. But we flipped it because, so now when you flip it, it's an exothermic reaction because we flipped the sign. Okay? Again, this brings us to a closer look, which allows us to look at enthalpy as a guide in a variety of things. Again, it's worth reading through and just to look at things. So We will take it a step farther once we continue on with the next portion.